Welcome to section 3.3, where we will be discussing the rules for differentiation. In other words, what we have to do to a function, what steps we have to take to get a derivative function from another function. Now, these steps vary in difficulty. They can be very simple or very complicated. It all depends on the function that we are differentiating. Now let's take a look at a very simple function here. We have x squared, which forms this nice parabola. As I follow this parabola with my cursor, we can see that for every x value, we have a tangent line, and every tangent line has a certain slope value. And if we plot the slope values of each of these tangent lines, we get a function that looks a little bit something like this on the bottom here. We get g of x, this red line. So at every point on f of x, every x value, we have a tangent line that has a certain slope. And if we graph those tangent lines here on the bottom, we get a straight line. Now, that straight line in the red is known as the derivative function of f of x. It's the derivative function. Now, you might ask yourself, is there an easier way to find that derivative function besides individually plotting each and every one of these tangent line slope? And the answer is yes. We can actually manipulate x squared, f of x equals x squared. We can manipulate that using a set of rules called rules for differentiation in order to get the equation of this line right here, which is the derivative function of f of x. There are various rules that we can use to differentiate a function, and which rule we use is completely dependent on the original function that we are differentiating. Rule number one is the derivative of a constant function. If f is the function with the constant value c, then dx is equal to dx of c, which is equal to 0. So in other words, this is saying that if we have a function that is just a constant, and we derive that function, then the derivative function is going to simply be 0. So let's take a look at what that looks like. So here I have the function f of x equals 1, which is just a straight line. Now, when I follow the line with my cursor, each tangent line is going to just also be a flat line. It's going to follow this function. And the slope of that tangent line, of each of those flat tangent lines, is going to be 0. So the derivative of any function f of x that is just a constant is going to be 0. And we can see that right here, this red line below is just g of x equals 0. So the derivative of any constant is just going to be equal to 0. So we can test that with various different constants. Here we have f of x equals 1. We can try that with f of x equals 2. And again, we have the derivative equaling 0 at every x value. F of x equals 3, same exact thing, except we can't really see it. One moment. So anytime you have a function f of x that is equal to just a constant, we know that the derivative at each point on that line is going to be 0. Next, we have rule number 2, which is the power rule for positive integer powers of x. If n is a positive integer, then the derivative of x raised to the n is equal to n times x raised to the n minus 1. So let's take a look at another example. Again, here we have f of x equals x squared. And if we were to apply the power rule that we just saw to x squared, then that would be the derivative of x squared would be 2x. And indeed, if we take a look at the derivative function here below, we see that the equation for this line, for this derivative function, the equation is just 2x, y equals 2x, or g of x equals 2x. Next up, we have rule number 3, which is the constant multiple rule. So anytime we have a function, let's call that function u, and we have a constant in front of the function, we can pull the constant out in front of the derivative function. For example, Here I have my function f of x equals x squared. Now let's see what happens if we put a constant in front of the x squared term. Look at the red line below, the derivative function of x squared. If I put a 3 in front of it, the derivative of the x squared is still going to be 2x. However, when that 2 is pulled out in front, we have 3 times 2, which is going to be equal to 6x. Next, we have rule number 4, the sum and difference rule. If u and v are differentiable functions of f, then their sum and difference are differentiable at every point where u and v are differentiable. At such points, we have d dx of u plus or minus v is equal to du dx plus dv dx. So basically that's saying if I have two different functions, if I have f of x is equal to two different functions of x, then I can just individually take the derivative of each of those. We will see some examples of this later on in the series. Rule number 5 is the product rule. The product of two differentiable functions u and v is differentiable, and d dx of u times v is equal to u dv dx plus v du dx. Basically what this means is that if we have two different functions of x that are multiplied together to form one big function, and we want to find a derivative of that, we're going to have to take the derivative of both of those functions independently and then multiply them by each other. Multiply the derivative of one by one function and then do the same thing for the other. And that looks a little something like this. So as you can see here, if I want to take the derivative of two functions, f of x and g of x multiplied together, first I have to take the derivative of f of x independently and also the derivative of g of x independently, and then multiply each of those derivatives by the other function and add those two things together. And again, this is a little bit hard to visualize here, but we'll have a lot of examples later on in the series where we can see this in action. Rule number 6 is the quotient rule. It's very similar to the product rule, except instead of having two functions multiplied by each other, we have one function divided by the other. We have to take the derivative of both the numerator function and denominator function, and then put it into this form in order to find a derivative function. Again, we will have some example problems later on in the series where we can see this in action. Next up we have rule number 7, the power rule for negative integer powers of x. This is basically the same as the original power rule, it's just applied when you have x raised to a negative number, as long as that number is not 0. For example, if we have the function x raised to the negative 1, then the derivative of that function is equal to negative 1, because that negative 1 gets pulled out in front, negative 1 times x raised to the negative 2. Remembering that this is true for all integer power values that are not 0. So if you have x raised to the 0, then you cannot apply this rule. Next, we're going to talk about second and higher order derivatives. The derivative of y prime is equal to dy dx, and this is called the first derivative of y with respect to x. Now, you don't just have to stop there. You can actually take a derivative of a derivative, as we see here. So if I take the derivative of y prime, then I have just found the second derivative, which is sometimes denoted as y double prime, or it can also be denoted like this, where we have d squared y divided by dx squared. And this is again known as the second derivative. And you can keep taking derivatives of derivatives as much as you want. Now, if you keep taking derivatives, eventually it's going to look a little bit strange if you have 4 or 5 different apostrophes here. If you have y triple, quadruple, or y fifth prime. So it's much easier to just label your derivative like this, using the Leibniz notation. For example, as you can see up here above, if I wanted to, for whatever reason, take the 7th derivative of y, it's a lot easier to write it like this than it is to write y and 7 little marks here. That's why in many cases, Leibniz notation, aka this one right here, where we have dy dx, is preferred to using these notations right here, where we have y multiple primes. These are just a few rules for differentiation. We're going to be covering a lot more of them, but these are the basic ones that you need to get started when doing calculus.